what's up, everybody? We are back on the heart. So, what we got to do is keep talking about cardiac muscle cells. And we were just doing contractile cells last time. And what we got to do now are the autorhythmic cells. So, autorhythmic cells are maybe about 1% of your cardiac muscle cells. And what's cool about them, I mean, their name implies this, they set the rhythm of the cell, of the heart, okay? They're going to control the heart's rate intrinsically. Now, obviously, there's outside influences that can affect the heart rate, chemicals in diet, um, your brain, nervous system, endocrine system, they can all affect your heart rate. But even with all those things removed, your heart can still beat. All right, you can rip a heart out of someone's chest, hold it up, like in this Indiana Jones movie screenshot right there. Hopefully, you know what that is. If not, you need to go watch it. And the reason the heart can do this, as long as it's got oxygen, is because it has autorhythmic cells. And what autorhythmic cells do is they spontaneously and rhythmically depolarize. And that depolarization then spreads to all the contractile cells because they're all linked by gap junctions. And that lets the contractile cells contract at the rate set by the depolarization of the autorhythmic cells. And the autorhythmic cells are all these yellow areas here. These were refined autorhythmic cells. All right, there's actually 6 groups. Group number 1 is up in the right atrium near the superior vena cava. It is known as the sinoatrial node. And as we'll see, it's pretty important. As the arrows show us here, and the fact that it's number 1 means it is going to be the initiator of the depolarization wave. In other words, it is going to be the pacemaker. Now, from the sinoatrial node, the signal spreads to our next group, which is the atrioventricular node, kind of a little lower in the right atrium. Then there is a kind of barrel-like grouping of cells called the atrioventricular bundle that lives up to its name as it spans both the atrial and ventricular walls. And that splits going down the ventricular septum into the right and left bundle branches. The moderator band actually extends off of the right bundle branch. Then down the ventricles, we get this elaboration of these last groups of autorhythmic cells, and those last autorhythmic cells are called the Purkinje fibers. Okay, from fastest to slowest, as far as the rate of depolarization, the SA node is the fastest, followed by the AV node, the AV bundle, and the bundle branches and the Purkinje fibers. So the pace is going to be set by the fastest group of cells, which is the SA node. And the SA node is therefore, as we mentioned already, known as the pacemaker. All right, quick question here. I want you guys to do this in class. And now let's walk through the actual pathway. If we start, which we will of course, starting up here at the SA node depolarizes first. Okay, then the depolarization spreads throughout the atria. The yellow color indicates the spread of the depolarization, spreading through gap junctions. Now the depolarization is also spreading towards the AV node. Now here's something very important. The wave of depolarization slows down at the AV node. There's actually fewer gap junctions there, which creates a bottleneck effect. And the depolarization, the electrical signal, slows down a bit. And what that is going to do, it's going to create enough time for the atria to contract before the ventricles do. That way the atria can top off the ventricles. And I had some air quotes around the words top off. The atria can top off the ventricles so that they're nice and full, or as full as they can be, prior to their own contraction. So that atrial node delay is pretty important. All right, so now check this out. The red color of the atria indicates they're contracting, but the ventricles have yet to contract. They're not red yet. Okay? They're not red yet because of that AV node delay. Now the AV node then allows the signal to pass to the AV bundle and down the bundle branches. Now what I want you to notice here is the directionality. Okay, notice that the signal is going down the septum. The signal did not go down the right side, did not go down the left side, did not go down the back, and this heart has been sectioned so we cannot see the front, but the signal did not go down the front either. The signal only went down the septum. Now, there's an anatomical structure that forces this pathway, and it's actually one we mentioned in the last lecture. It is the fibrous skeleton of the heart. The fibrous skeleton of the heart forces the electrical signal down the septum. And what this means is we have to go down the septum, and then from the apex, the electrical signal hangs a U-turn and goes up the ventricles. So the depolarization goes from the apex up. Now, why do we do this? Of course, there is a reason. And a great analogy to this is a tube of toothpaste. Think about the proper way, the civilized way, if you will, to squeeze a tube of toothpaste. You squeeze from the bottom because the exit is at the top. Same thing for the ventricles. Notice the red starts down here at the bottom at the apex. So the squeezing force is going to go from bottom up. And this makes sense because the pulmonary trunk and the aorta are at the top. So we got to start squeezing from the bottom. All right, that is the basic pathway of both electrical activity and contraction in the heart. All right, so we were just going over the intrinsic controllers of heart rate. In other words, the SA node and its fellow autorhythmic cells. There are, of course, extrinsic controls. Let me mention that the SA node's default rate of depolarization is about 100 beats per minute. Okay? That's the default rate. That's if nothing else is going on. But your heart rate is probably not 100 beats per minute. It's probably less. Take 10 seconds, count the number of pulses you feel, multiply by 6, and that is going to be your heart rate. All right, I'm doing this as we talk right now. So my heart rate's about 54 beats per minute. So that's lower than the default rate of the SA node. Now, why is this? Well, that's the influence of the endocrine and nervous systems. All right, and we're going to see why at the moment. If you're sitting down, I'm sitting down right now. I'm getting a little excited. I'm sure you are too. But you're still probably less than 100 beats per minute. And that's what we got to figure out now. So there's actually two regions in the medulla oblongata that we have to be aware of. There is a cardioacceleratory and a cardioinhibitory center. The cardioacceleratory center consists of these cardiac sympathetic nerves that come down to the heart. They innervate the SA node and AV node and thus increase the rate of the heart's contraction. They also innervate the ventricular myocardium and increase the heart's contractile force. Now, they're able to do this by releasing good old norepinephrine, remember our sympathetic neurotransmitter, onto the heart. Now, meanwhile, our cardioinhibitory center is going to travel, or send signals rather, down the vagus nerve, cranial nerve number 10, down to just the SA node and the AV node. And when it releases acetylcholine, our parasympathetic neurotransmitter, that causes heart rate to drop. Okay, check out this car. Here's a picture of my car. Ignore the license plate there. And there's a brake and a gas pedal. Realize that most of the time we are using the brake pedal. In other words, the sympathetic influence on the heart at rest is much greater than the The parasympathetic influence is much greater than the sympathetic influence. So at rest, your heart rate is much lower than that default 100 beats per minute. Now, of course, during exercise or a stressful situation, that flips. And that resting dominance of the parasympathetic system is known as vagal tone. Vagal tone. All right. Last slide here. Questions. We'll cover these in class, and I'll see you guys later. Adios.